On November 5th, new observations of Atlas were released, and instead of bringing clarity, they raised more questions. The images show a compact point of light, no visible tail, and almost no change compared to earlier readings. For an object that should be shedding material near the sun, this behavior doesn't fit. The data keeps pointing to something we don't fully understand. And by the end of this video, you'll see why scientists are paying very close attention. Since the last video, the most important development has been the new observational data. Not new in the sense of discovery, but new in terms of what it reveals about Atlas's behavior. Several telescopes have now gathered updated brightness measurements, thermal readings, and trajectory corrections. And while the expectation was that these numbers would gradually confirm the natural explanations already being discussed, the opposite happened. The data only deepened the inconsistencies. The projected model suggested Atlas should have shown more visible activity by now. The amount of mass loss needed to account for its current acceleration is not a small adjustment, it's substantial, which means there should be clear, observable changes in its outer material and brightness structure. Yet the object remains visually compact, almost static in appearance, even after passing through regions where we would normally expect increased surface activity. This isn't a case of missing a detail or needing better resolution. The observations are coming from multiple independent teams with instruments capable of detecting far smaller variations than what should be present here. The object should look different. It should show signs of the energy expenditure required to maintain the trajectory it's currently on. But it doesn't. And this is where the scientific tension forms. Not because Atlas is behaving dramatically, but because it's behaving too consistently, too controlled, too unchanged for the conditions it's in. The recent data didn't clarify the situation, it brought the underlying contradiction into sharper focus. So at this point, the question is no longer whether the anomaly exists, it's already measurable. The question is what's sustaining it and why the expected physical signatures are still missing. Since the previous analysis, the trajectory updates have confirmed something that wasn't clear earlier. The additional acceleration affecting Atlas has not tapered off. Even after perihelion, the point where many objects begin to stabilize as surface activity declines, the deviation from the purely gravitational path has continued. The displacement is now large enough that it can't be dismissed as measurement noise or model adjustment. It's persistent, measurable, and growing over time. This continuation is important. Temporary deviations are not unusual when observing distant objects under thermal stress, but sustained acceleration requires a sustained source of force. And if that source were tied to material release, then the physical appearance of Atlas should reflect that by now. Yet the new imaging and brightness profiles show no significant structural change. The object still appears compact, uniform, and sharply defined, with no expansion of surrounding material, no diffuse halo, and no observable variations in surface reflection patterns. The data sets from different observing groups align on this point. When plotted against time, the acceleration curve maintains itself rather than declining. When plotted against luminosity, the profile remains consistent rather than broadening. These are not ambiguous results. They're stable across instruments and observation windows. This leaves researchers with a clear tension. The measured force implies ongoing mass loss, but the visual and spectral data do not show the effects of that loss. The conditions necessary to sustain this acceleration should leave a signature, yet that signature is absent. So at this stage, the discrepancy is no longer about whether something unusual is happening. That part's established. The focus now shifts to understanding why the expected physical response hasn't appeared. And this was only the beginning of the inconsistencies. We already covered what should happen to brightness as an object approaches the sun, so we won't go over that again. The important update here is how Atlas's brightness has changed over time, and how that change refuses to match the physical conditions we're observing. The new brightness measurements show a curve that rises far more steeply than expected. Not just a stronger increase, but a highly consistent one. Instead of fluctuating or leveling out as surface material responds unevenly to heating, the brightening has followed an unusually smooth, continuous climb. In natural objects, brightness change almost always shows some irregularity. Atlas's curve, by contrast, is clean. This smooth escalation matters because a rapid increase in brightness normally corresponds to the release of material, dust and gas spreading outward and scattering sunlight. But Atlas continues to appear compact and sharply defined. There is no diffusion pattern, no extended halo, no widening of its light profile. The brightness is rising, but the object is not becoming visually softer or more dispersed. In other words, the luminosity increase is happening without the visible mechanism that would typically produce it. Multiple independent teams report the same pairing, steep brightening, stable structure. And the longer this pattern holds, the harder it becomes to explain through temporary effects or measurement variation. The numbers say one thing, the images say another, and they do not align. Then came the color, and that raised even more questions. One of the most striking updates from the recent observations has to do with Atlas's color. When the new spectral data was compared to earlier readings, researchers found that the object appeared noticeably bluer during its closest approach. Not slightly shifted, distinctly blue in a way that stands out even when measured against the sun's own spectrum. This matters because temperature and color are closely linked in astrophysical observation. Cold surfaces typically emit light in the redder end of the spectrum. Warmer sources shift toward white or blue. Atlas, based on its estimated surface temperature and distance from the sun, should fall firmly on the redder side. Instead, it reflects more strongly in wavelengths associated with significantly higher energy emission. There are natural processes that can create this effect. For example, certain ionized gases can emit light in the blue range when they are energized. CO+ emissions are one candidate that has been suggested. However, this explanation leads to another inconsistency. If ionized gas were producing this color signature, there should be a surrounding plume or extended emission region visible in imaging. So far, that hasn't been detected. The color shift is present, but the spatial structure that should accompany it is not. This is why the color data has drawn attention. It's not just that Atlas appears blue, it's that the mechanism required to create that signature is not showing itself in any of the expected forms. The brightness profile remains compact, the surface reflection remains tight, the energy is expressing itself without the dispersion that should naturally accompany it. So once again, the measured output and the visible structure don't align. The numbers point one way, the images point another, and the gap between them continues to grow with each round of observations. But the anomalies don't stop at appearance, they extend to its path. The next point focuses on Atlas's trajectory. As we mentioned before, its path aligns almost perfectly with the ecliptic plane, the thin, disk-like region where nearly all planets orbit the Sun. That alignment was noticeable early on, but the updated tracking data has shown just how precise that alignment actually is. It isn't loosely close to the plane, it's tightly confined to it, maintaining a level of orbital consistency that is statistically uncommon for an object arriving from interstellar space. Interstellar objects typically enter the solar system from arbitrary angles. Their approach vectors are random because they originate from entirely different stellar environments. There's no reason for them to match the plane of our system unless the alignment is the result of coincidence. And while coincidence is possible, the probability of an object approaching with this degree of planar precision is very low. Not impossible, but highly unlikely. There's also the matter of timing. As Atlas has continued along its path, its closest approaches to certain planets have occurred at moments that appear unusually well aligned. It passed near Mars and Venus at points where the observational vantage and orbital geometry minimize direct viewing from Earth. Meanwhile, its eventual approach near Jupiter is projected to occur during a window of increased scientific interest, simply because the object's changing acceleration has already drawn ongoing monitoring. This sequence doesn't imply intent, and it doesn't require assuming purpose, but it does highlight a pattern that doesn't match what we would expect from random interstellar arrival. The alignment, the timing, and the observational geometry all stack together in a way that stands out when compared to known incoming objects. None of this provides conclusions on its own, but it adds another layer to the growing list of mismatches. And the composition only complicates the story further. The composition question is now one of the most actively discussed aspects of Atlas, but not because of a confirmed result, rather because of the lack of consensus. Several research groups have released preliminary spectral analyses suggesting an unusual distribution of metals on the object's surface. However, those results are not uniform. Different observatories are reporting slightly different ratios, and the margins of uncertainty are still wide enough that no definitive conclusion can be drawn yet. This is important to emphasize clearly. Nothing about the composition is confirmed. The readings are based on reflected light collected under different atmospheric and instrumental conditions and processed through models that are still being adjusted. Even small calibration differences can shift the interpretation. For now, what exists is a pattern of suggestive data, not a verified result. But this ongoing debate matters because of the context in which it's happening.
If the readings were simply unclear or noisy, they would likely be dismissed as routine observational variation. Instead, the discussion is happening precisely because the signals appear to fall outside what researchers expected, and because those signals line up with a broader series of inconsistencies already surrounding Atlas. So the real significance here isn't a claim about what the object is made of. It's the fact that multiple teams are examining the same question and arriving at slightly different outcomes, each of which raises more questions than it answers. The disagreement itself is the story. The data is complex, the interpretation is unsettled, and the community has not reached a unified view. In other words, the composition remains an open case, one that could shift in either direction as more precise measurements come in. But the biggest moment of truth hasn't happened yet. All of the unanswered questions surrounding Atlas are now converging toward one key moment. Over the next observation window, particularly as Atlas reaches its closest approach, multiple major telescopes will be collecting coordinated data. Ground-based observatories, space telescopes, and interferometric arrays will all be watching the same phase of the object's trajectory, looking for one thing above all else: evidence of sustained mass loss. If the acceleration we've been tracking is being driven by outflow of material, then the volume required is not subtle. It would have to be large enough to produce a significant surrounding cloud, something that should be unmistakable when viewed at this proximity. We are not talking about a faint halo or borderline signal. The predicted mass loss would create a widespread, luminous envelope that even moderate telescopes could detect. And this is where the situation becomes decisive. Because if that cloud appears, the natural interpretation stands. The acceleration can be explained, the brightness profile fits within expectations, and the earlier discrepancies can be attributed to timing and observational limitations. But if the cloud does not appear, if the object remains visually compact and stable at closest approach, then the natural explanation fails to account for the forces at work. At that point, the discussion shifts from what is happening to what is causing it, and the set of possible answers becomes much narrower. This upcoming window is not about speculation or interpretation. It is about direct observation. The results will either reinforce the current model or leave a gap that cannot be explained with known physical processes. No one can say yet which outcome will emerge. We are simply approaching the moment where the data will speak for itself. And what comes after depends entirely on what we see next. So at this stage, the conversation around Atlas isn't about naming something extraordinary. It's about acknowledging that the data hasn't settled into the explanations we expected. The acceleration, brightness curve, color signature, trajectory alignment, and composition debate all point to patterns that don't fully match standard models. None of this proves anything on its own, but taken together, these details form observations that can't be ignored. The key now is the observation window ahead. The closest approach will give us the clearest view of whether there is a large-scale release of material, and that single observation will either confirm the natural explanation or push the discussion into new territory where the current assumptions are no longer enough. This isn't about deciding the answer early, it's about following the evidence. And when the new data arrives, everything comes down to one question: does Atlas show the mass loss needed to explain its motion, or not? If you want to stay updated as the new observations come in, make sure you are subscribed, turn on notifications, and leave a comment with your thoughts so far, especially which explanation you currently find more convincing and why. Because the next set of images may change the discussion completely. Thanks for watching, and see you in the next video.